Lesson 3.4, this one is about velocity and other rates of change, motion along a line. We'll look at an example in econ using derivatives, because I know a few of you are taking econ classes currently. So instantaneous rate of change, we understand that instantaneous rate of change is talking about the first derivative. And when we say rate of change, we really mean the instantaneous rate of change. We know this is the formal definition of a derivative, and let's take it away. If the area of a circle as a function of radius is written as a equals pi r squared, Part A says to evaluate or find the rate of change of area with respect to radius. So I'm going to interpret this as being the instantaneous rate of change. So I'm going to say A prime is equal to 2 pi r. And it said with respect to r. So I could have written this as dAdr equals, and then I could have 2 pi r. So the derivative of area is circumference. Nice. B, evaluate the rate of change of area when r is 4. Oh, that's not so bad. So I want to look at the rate of change of area when r is 4. So that's that nice notation there. And I'd have 2 pi times 4, so I'm getting 8 pi. And what would the units be? They didn't give us any units. I guess we'll skip that. It would be units per time, whatever that happened to be. And then part C, using the formal definition of derivative, find the rate of change of area with respect to radius. Well, that's going to come back and be the same. I'm going to pass so that we don't spend too much time doing this. This is not in your notes, so I'm going to pass on that one too. Let's talk about vertical and linear motion. Just a good review of AB. Speed is the absolute value of velocity. So speed can be written as the absolute value of v of t, which is equal to ds dt, the derivative of the position function, not derivative of speed. So ds meaning position here. Displacement of an object over time is the amount of distance it changes. So it's change in position. Here it's using f of t plus some change of t. So some time in the future minus the original time. We could think of it as s of t sub 2 minus s of t sub 1. And that gets us the change of s. So it's change of position. How far did it move? Instantaneous velocity is the derivative of the position function with respect to time. At time t, the velocity is ds dt. We know velocity is the first derivative. This is just formal definition of derivative. Probably don't need to have that. Average velocity, this one people have trouble with. The average velocity of an object over time is going to be how far it moved, so it's change in position over its change of time. So we think of it as displacement over the time traveled, or the change of time. Change of position over change of time. You could write it in the function notation, but that might be more confusing. Acceleration. Acceleration is the derivative of velocity with respect to time. If a body's velocity at time t is v of t, which is the derivative from position, then the body's acceleration at time t is dv dt, is what that says. Or we sometimes write it as v prime, which is two derivatives off of position. Vertical motion. For velocity of a vertical motion, positive velocity is upward motion. How do I want to write this? V of t greater than 0 means that it's going up. V of t less than 0 means the particle is going downward. If I in a linear or a horizontal motion style, v of t being greater than 0 means it's moving to the right. And if v of t is less than 0, I know my object is moving left. I think most of us are pretty clear on that. Number 10, on the back side, it says, a particle P moves on the number line shown in part A with the accompanying figure. Part B shows the position of P as a function of time. So we've got horizontal movement, it looks like, for part A, and it shows the position, so the number of centimeters that it moved according to time, our independent variable. Part A says, when is the particle moving to the left? So I'm going to focus on my position function. When would it be moving to the left? Well, I need to know when the velocity is less than 0, which means I'm looking at when is s of t, if it has a negative derivative, if s of t has a negative derivative, that means that s of t must be decreasing. Where do we see s of t decreasing? Right here, correct? And that is over the time span of 2 seconds to 3 seconds. Oh, I lost the other one. Surprise! I didn't look well enough. There was one more decrease, wasn't there? Position was decreasing. That would be negative slope, which means we have negative velocity, and they are moving left. When's it moving to the right? Well, contrapositive here. V of t is greater than 0, which means that our position function is increasing. If I were on the AP exam, I would need to state it in that terms because I am not looking at a velocity graph. I have to write it in terms of what I see, which is position, and this position is increasing. And let me see if I can get this one right. I see increase only from time 0 to 1. Yay! Woo! When is P standing still? Well, P is standing still when the position is unchanged. S of t is unchanged. And that would be these horizontal spots where they stay either at 2 centimeters or negative 2 centimeters. So whatever those time frames turned out to be. From 1 to 2 it says, and 3 to 5. That one's not so bad, is it? Okay, part B says graph this particle's velocity and its speed. So the velocity would be the slope of position, wouldn't it, of s of t. And speed would be the absolute value of v of t. I think I'll work with velocity first. I need to calculate some slopes here. This looks like it has a slope of going up, rising to, and then it went, I should write it here, up to over 1. So we have a slope of 2, we have a slope of 0. This goes down 4, right 1, so minus 4 over 1. This has a slope of negative 4, and this has a slope of 0, and this drops down by 2 over by 1. So this has a slope of negative 2. Now all I got to do is let's graph that. So from time frame 0 to 1, our velocity is 2. From 1 to 2, velocity is 0. From 2 to 3, velocity is negative 4. From 4 to 5, velocity is back to 0. And 5 to 6, velocity is at negative 2. So my blue represents the velocity at the particular time. Now to do speed, it's going to be easy. It's the absolute value of velocity. So this will come out as a 4 and a 2. And my pink is speed. So if the question asks when is it moving the fastest, I would have to answer that it is moving the fastest on time frame 3 to 4. Even though it's a negative, that just means it's moving to the left, but its speed is at its highest point on that time frame 3 to 4. I don't know that you have this picture. A particle moves along the x-axis so that the position 0 to 18 is given by x of t, whose graph is shown below. The inflection points of the graph are marked with green circles. Find all intervals of time when the speed of the particle is decreasing. Oh, that's a tricky question. Speed is decreasing. So I want to know when this is slowing down. And the particle is slowing down when velocity and acceleration have opposite signs. And what were we given? A particle moves is given by x of t. So, and the inflection points are marked with green. So we're looking at a position function. And the, what do we want? Slowing down. This is so there's two things I'm going to look at. I want to look at velocity, which is really the slope of x of t. And then I want to look at a of t, the acceleration, which is really, when I'm looking at position, the concavity of x of t. So I need, if my slope is down, so v of t is less than 0, it's negative, then I would need opposite, I need concave up, I need a of t to be concave up. And this is concave up. So from time frame 0 to 5, I believe we have a negative velocity. So I would say from 0 to 5, we have v of t greater than less than 0, and a of t being greater than 0, concave up. Then I am in v of t being positive, but concavity is positive there, but then it goes into a negative. So until I reach the max here, I have slowing down as well, because I have v of t being positive and concavity being negative. So time frame, what time frame is this? From the point of inflection, 6, to 8, I'm going to have a v of t that is positive and an a of t that is negative, concave down. Concave down with negative velocity, that would be speeding up. Concave up with negative velocity would be my time frame, and that's going to be from there to there, I'm going to say 10 to 12. So on the time interval 10 to 12, it is also slowing down because v of t less than 0, but a of t greater than 0. Lots to read. We can get a lot of information off of a position function. All right, I'm not going to go through that one. Let's go continue on. Should we do this one? Sure. This one's not too hard. Got a thoroughbred racing. A racehorse is running a 10 furlong race. A furlong is 220 yards, although we will use furlongs and seconds as our units in this exercise. As the horse passes each furlong, a steward records the time elapsed since the beginning of the race as shown in the table. So this is elapsed time here. And then we got furlongs, how the distance traveled on the top. How long does it take the horse to finish the race? Well, we can look at the elapsed time and see that it's 1:35. So this 1:35 looks right to me. What is the average speed of the horse over the first 5 furlongs? And it asks for average speed. So we want to take the position S of 5 minus S of 0 over the time frame 5 minus 0. So we're looking at displacement over change of time. And at 5 it was 73. Oh, I'm reading this backwards. I want this to be written differently. Change of distance is 5 minus 0, and the elapsed time was 73 minus 0 seconds. Ooh, almost had my labels flipped upside down. This was furlongs. So we'd have 5 over 73, which is about, oh, I do have it, 0.068 furlongs per second. Part C, what is the approximate speed of the horse as it passes the 3 furlong marker? So now it wants more of a instantaneous velocity, but I don't have a derivative to take, so I'm just going to have to approximate it. And I'm going to do that by centering myself over 3 furlongs. So I'm going to look at the 2 closest numbers I can gather, and I'm going to have change of position, 4 minus 2, over change of time, 59 minus 33 furlongs per second. Looks like we're getting 2 over 26, or 1/13, which is about, I did calculate 0.077 furlongs per second. So it's going faster at 3 furlongs than what it did. But that was an average from 0 to 5, so that's kind of hard to compare. All right, during which portion of the race is the horse running the fastest? You can check it out. It's near the end of the race. All right, enough on that one. The last thing is the little econ application. Economists have a specialized vocabulary for rates of change and derivatives. They call them marginals. In a manufacturing operation, the cost of production, C of X, is a function of X, the number of units produced. The marginal cost of production is the rate of change of cost with respect to the level of production. So we can talk about the derivative of cost with respect to the units, dx. The change in units. Sometimes the marginal cost of production is loosely defined to be the extra cost of producing one more unit. So the example says, suppose the dollar cost of producing X washing machines is C of X. Here's our cost function. Find the marginal cost of producing 1,000 washing machines. So the marginal cost is the derivative. So we're going to have dc dx is equal to a 0, and then it'll be a 100 minus 0.2x. And then it wants us to find it at 100 units. So this marginal cost of producing one more unit beyond the 100th unit could be calculated as such. Looks like it will cost us $80 additionally to make that 101 unit. it's kind of cool to see that business side of things uses calculus as well. And so if you're a person that's interested in business but love math, this should be right up your alley. That is all for today. Um, that is an old Math Excel assignment, so I will be generating a WebAssign that hopefully I can find some of these same problems in WebAssign. So stay tuned. I'll post on Schoology what your assignment is. Bye-bye.